Hello everyone and welcome to my channel. In this video I would like to investigate how to install 386 BSD on a 386 machine, a real one. Okay, let's get started. This video is going to be split in a couple of parts, and as a warning before, I've not scripted the video, mistakes will be made and they will be part of the video. Also, before I start the installation and showing everything, let me just say that unfortunately I've been a little bit busy these last few months at work, and this means that my video production has been quite severely lowered, but I do hope to be able to produce more videos when time allows. I hope that July this year things are going to be normal a little bit again. Alright, so this video is going to be split more or less into two parts. The first part I'm going to show you how to install 386 BSD based on an ISO image, on a CD-ROM image that I've created. This CD-ROM image contains a new bootloader that I also created myself and the kernel that has been fixed by myself. Basically, if you have seen some streams I've done before, you might have seen that the kernel, the 386 BSD kernel that I have, is a slightly modified version of version 1.0 from the original 386 BSD, where I tried mostly to fix bugs to make it stable and just added one or two features. One of the features that I've added that I definitely wanted to have in the first version that I release is the support for an IDE ATAPI CD-ROM drive. The original 386 BSD kernel was only booting from a SCSI drive. This means that if you want to boot the CD-ROM in actual hardware, you should be able to do it much easier because you don't need an Adaptec SCSI card with a CD-ROM. Those are possibly pretty expensive to get vintage, but if you have a regular ATAPI CD-ROM that connects to the ID drive, it should boot and you should be able to install and enjoy 386 BSD. One small remark, I developed also this logo. Yes, it is. This logo was AI generated, but as far as I understand, in the website that I used, this logo is also even allowed for commercial usage. The logo represents a phoenix rising from the ashes, which is what I'm trying to achieve here. Right? Also, as a very small detail, it contains the yellow color because I like yellow, and that's the justification of it. Okay, so first step, the hardware that I'm using is a 386 machine that has been expanded to its maximum capabilities. The motherboard supports 32 megabytes, not gigabytes, no, megabytes maximum, and I've expanded it to 32 megabytes. And I've also increased the cache size to the maximum allowed by the motherboard, and currently it has amazingly 256 kilobytes of cache memory. In the streams I've been doing, you might have noticed that I was using a floppy drive, and that the machine itself has a 8 gigabyte hard drive that I will not be using because I decided to buy a Gotek floppy drive emulator. Makes things a little bit easier. And the ID drive I'm going to be using is from AliExpress. I bought CF card to IDE, and I'll be using a relatively small compact flash card, huge for its time when 386 machines were roaming the earth. It's an amazing 2 gigabyte compact flash card, and we'll be installing 386 BSD in that drive. But before we do that, we need to know what are the number, how many cylinders, how many heads, how many sectors do we configure in the BIOS. So let me pull out the disk utility here we see that, so I've connected the compact flash card to my Mac, and let's just go here to get information. And we see that the volume capacity raw is this value here, 2097930240. Okay, so this is the 2 gigabyte value. And let's convert these to cylinders, heads, and sectors. For that, I show you a small computation here. The number of sectors is the size, the number I just read back to you, divided by 512, which gives the number of sectors here. So 4,097,520. And I'm going to be using the maximum value allowed by the BIOS for the heads and sectors. This means 16 heads, 63 sectors per track. And this means that we need to compute the number of cylinders. And this is going to be the number of sectors divided by 16 times 63. And we come to the value 4065. So our configuration is going to be cylinders, heads, and sectors, 4065, 16, and 63. All right, with these numbers in hand, we are ready to boot the machine and configure the BIOS. Here, as you can see, I'm booting the 386 machine with the real hardware, and I press the delete key to enter the BIOS. The machine still counts the memory. The machine has 32 megabytes of RAM, and we're going to enter the BIOS in soon. Okay, here we go to the standard CMOS setup, and under the hard disk, the type 47, we put in the number of cylinders, 4095, heads 16, sectors 63, L zone is the landing zone. For this case, we don't really need. The floppy B, we can just leave it as no installed. And here it's important to confirm that the boot sequence is set to A and C. I adapt a little bit the monitor, so the capture card. And you might have noticed now that for the first time in my channel, in all the videos I've done, I'm now doing a voiceover. So let's see how this goes. All right, so we write the settings in the BIOS, and the next step is to use the Gotek floppy drive emulator, putting an image to boot the 386 BSD kernel. This is going to be provided in the CD-ROM. And in this case, I look at the ff.cfg. If you have a Gotek, this is the most important configurations are here. And as you can see, host equals PC-DOS. That is the most important thing, to say that the Gotek simulates an ID drive. The next thing is my display is inverted. It's upside down. So I set the setting to rotate, and the display looks pretty cool, pretty nice. Next thing, we copy the DE kernel variant. That is the kernel which contains the German keyboard, because my keyboard has the German variant. And I plug in the USB into the Gotek drive, and I reboot the machine. If you remember, the floppy sequence for boot is A and then C. C drive currently contains nothing, and therefore we pick up on the floppy A, which boots on MS-DOS 5.0 with MSEDEX and the OTI driver, which is for the CD-ROM. So we can see here the CD-ROM is there. I burned this CD-ROM, so it's a physical copy. And I provide the command boot.exe, which I will be describing at the end of the video. So stay tuned. At the end of the video, I describe this. The boot requires a kernel, which is also provided in the CD-ROM, and a root file system, which could be an IDE drive or a SCSI CD-ROM, and also requires the parameter -ISO file system. if you're booting from a CD-ROM. So let's write boot 386pst-r for the root file system, and here I make a small mistake, AS1D. This is not a SCSI drive, and we need to write the ISO file system. So I notice now AS1D is actually wrong because we have an IDE CD-ROM drive. So let's fix that. -r WD1D, the primary slave. It's configured like that, and it's an ISO file system, ISO 9660. Okay, let's boot the kernel. So it goes and starts, and it identifies WD0 as a compact flash card, 2 GB, and WD1 a CD-ROM drive on the ID. So I accelerate things a little bit. Here you can see that the ED0, it's the network card, has been detected. That's pretty cool. And just for the case, I'm going to wipe the disk before the disk. The compact flash card has nothing, but it doesn't harm to make sure that no partitions are going to affect us. So let's just try and run the installer with the commands. So first we see the files that are there in the CD-ROM, that's fine. And install -w for wiping. And -d for WD0, the first ID, the primary master drive. It asks us if we are sure, because we're going to be storing the data. Yes, we are sure, so please go ahead and do the business. All right, so now the disk is wiped, so the boot sector, etc., and we are ready to install. Basically I write zeros to the disk to make sure that it's initialized, that there is nothing in the disk. Now we just run install without any parameters, and this installer that I've created just tells us that this is going to be done in 5 steps, as you see in the screen, and you want to proceed with the installation, and yes, we want to proceed with the installation. The target disk where we want to install the system is WD0, the first, or the master, the primary master disk. So it's option number 3. It detects the parameters we set in the BIOS. It's 4065, etc. And there is no partition table because we wiped the disk. And if this is a clean card, it's going to show the same thing, which is basically nothing. And the first question is, do you want to use the entire disk? Just press enter. Yes, we want. And just use the recommended settings. So here we can just press enter to get, it's about 1.9 giga for the main partition, a very small swap, 64 megabyte, and we just format the disk. Here I accelerate things a little bit. It takes a little bit of time to format, but at the end it mounts under /target and gives us the options on the things that we can install. We can install the base system, x386, source, local arch, and I have a couple of packages which are pre-built, and I'm going to show you a couple of the goodies that I prepared. So we go to the pre-built binaries, and for example, we have bash, we have less, we have screen, we have vim. Those were things that were not in the original 386pst version 1.0, but I provide here for because it's pre-compiled. Y-tree, it's also a really nice program. And there are a couple more things. For example, in developer tools, we have Perl, TCL, TK. I'm just showing what is existing because at the end of the day, I'm going to install everything. So we just say Yeah, we have, oh, yes, exactly. We have window and screen. I think we saw screen before. I will be demonstrating screen later on in the video. So here it's cancel. The menu, the name of the menu is a little bit bad. Yeah, cancel just goes back. Here I select all the packages and 600 megabyte. And we just type the menu option 1, install the selected packages. At this point in time, the system is going to install everything, and as you can see in the video, it does look like this is going really fast, but let me tell you that I've accelerated this part really a lot. The process takes about 2 hours to install everything, and I think that I'm just showing you, giving you an idea about how the things are installed. I just do this in about 1 minute, but the whole installation process with the real hardware, yeah, we are back in time. It does take lots and lots of time. Maybe one way to accelerate that would be to create individual packages to install the things, because currently the system is just copying things from the CD-ROM and copying them recursively. Okay, it went a little bit fast, but it just did install the master boot record and unmounted the disk, and we can now shut down. The dash P, I forgot at this point in time, dash P does not exist in this version, so it should be dash H for halt. As a next step, we just reboot the system. All right, so here we are. Let me just center the screen a little bit better. All right, so we don't want to miss anything in the screen. We can just log in as root, and as you can see, we are in. Let's try the network card for the first time. So if config, we have ed0, and currently it's not configured. So let's say if config ed0 192.168.2. Let's get a static IP address here. So I'm just going to use 77 255.255.255.0 and root add default 192.168.2.1. And let's try to ping 8888. And here we are. We are able to ping the system, no problem. One thing that you might notice here is that the time 26 milliseconds is a little bit high. Mm. I'm not exactly sure what's so the mask. I'm not exactly sure what's happening, but as you can see here, so this is a clone of an E2000, the card that I have, and I sometimes the IRQ is not properly detected, and therefore I've implemented a mode that just says it's the polled mode. And yeah, it's a little bit slower, but the card still works. Good. I've installed quite a few goodies already. So Y3, for example, is already installed. You can see this is pretty cool. Okay, log slash. It's already pre-configured and should be working. But one of the things that I want to have, I want to use bash as my standard shell. So first, let's just start bash. There we are. And Vim, which is installed, we can go to etc, and there's shells, and we can add here /user local bin bash to the shells, and we can enable Vim as a shell in the system. Okay, file is read-only, so write with the exclamation mark and VIPW. And when we do this, we can see here that we have a C shell by default. we can say user local bin and let's put bash. Rebuilding the database, done. Before we start, let's go and edit I think it's the profile. We don't need this part here. I think here, let's just keep this for the time being, and let's add here export ps1 slash user at slash host slash w with a hash, and here, let's try this and exit. The first exit just exits to the normal to C shell, and we exit again. And let's try again. Root, login, and there we are. This prompt looks a little bit more familiar. All right, so another nice thing that I've installed was Screen, and here we can just press enter, and here we are inside Screen. Screen, why is it nice to use this? Well, we don't have several TTY, so Alt F1, Alt F2, and so on. Currently, it's not working in this installation, but with Screen, we can have several terminals, and this version of Screen works with Control A. So Control A H, it takes a, okay, that's not what I wanted, a question mark, yes, Control A question mark gives the help here. We can see this, okay, so space for next page. Yeah. So we can just, for example, start Y3 here in this one, in this screen, log slash, we can have this one, and Control A C to create a new one, and now we have two screens. Control A0, we go to the first one. Control A1, we go to the second one. Really cool, really nice. Of course, we also have Perl, but before that, let me just add it here, slash etc slash netstart. And I left already a couple of things here. Let me see. Yes, this is for 86 box, but we can have this done on boot 192.168.2, and I think I selected for this machine 77. My router is okay with this 192.168.2.1. Now we save this. Another thing we should edit is etc resolve. So resolve, and we can add here name server 8888 so that we can ping google.e. Also pretty nice. Control C. Okay, let's try to restart the system to see if it picks up the network card. So let's first exit from here, close this, and shut down -R now. All right, so we are there again. So one of the things we have here is, if you remember, we have Perl installed. So let's see version. We have Perl version, Perl-V. Yes, we have Perl version 4.0 from 1993. Let's try to do a small example with Perl. So make directory test, cd test, and vim test.pl, and let's just put here user local bin Perl, and let's create a subroutine called add values or add function, and let's get local value 1 comma value 2, and let's call it the sum. I think we can define things like this. Let's print uh, enter first number, and value 1 equals std in, and let's do a chop on the variable 1. Let's copy these lines, let's put them here, enter second number. Let's put this here for v2 and here v2. Oops, wrong one. And say that the sum is v1 plus v2, and finally print the sum is sum. And let's just add a caret return here, and let's just call this function. I think it should be called like this, add. And we can add a small comment here, call function. All right, so chmod plus x of this file, test, and let's try to run test. First number 2 and second number 7, the sum is 9. Wow, and I didn't make any mistake for the first time. That's really cool. All right, now probably you've been waiting for this. I'm going to try to start an X server. So for that, let's have a look at the following thing. So I think we should go here to the dot profile. Before that, let's see the directory. I think it's user x bin, and yes, there are a couple of things there. So user x386 bin, let's add this to the path. Vim dot profile, and let's just create. So let's say which FVWM is not here. So let's, I think it's rehash. I think it's called like that. No? Okay. Then let's just log out and log in again. Root and FVWM. Yes, it's there. Which, so it should be, no, it's not there. User contrib, it's still pointing to user contrib. Okay. Echo path. Well, we have here, it's interesting. No problem. User x386 pin FVWM. Is it here? Yes, it is here. So let's then just create .x init.rc. That is one of the important files we need. And let's say /bin/sh. And let's start an X term with the geometry of 80 times 50. I think we need to put +0 +0, do an n% and exec FVWM. So this looks already pretty nice. I think we might need this. Okay, xmod and vim user x386. I think probably it's under lib x11, and I think xconfig. All right, yes. And I think this is already okay for the graphics card that I have. So we have the RGB path, the font path. We have a keyboard. I guess that this is okay. We have Microsoft under mouse under /dev/com1. I have a Microsoft mouse on plugged into /dev/com1. Maybe I think the baud rate could be set. I'm going to, oops, changing read-only file. It should be fine. I think VGA 256 could be a good graphics card. Let's see. VGA 16 is probably want to deactivate this card. Let's start with 800 by 600. Let's see if we can get this, and let's put this thing here and say that we only want the 800 by 600 mode. We don't want any other modes. And the 800 by 600, I think the mode is already here. We could go by with 1280 and so on. Let's go with 800 by 600 for the time being. So save. Okay, save it like this. Exit. We probably need to adapt user x386 bin. What is X? Yes, it's pointing to XF86 VGA16, so we don't want that. Link, soft link of XF86. I think it's, let's see what is available. SVGA, I think it's the SVGA that I need. Let's put this to X. So if we look at here, this one, the X server should now be pointing to the correct one. Let's see. Yes, it looks good. Shall we try? Start X. Let's go for it. All right, really nice. It's looks a little bit strange with the menu, and the mouse is not working. So I think that was to be expected. Let's just it looks a little bit strange for you probably. It's the I need to try to fix that. So let me first try to kill the X server. Okay. Yeah, I should read things. 104. That's the one above. That should stop the X server. It's the very first line. Yes. Okay, somehow I got logged out. Let's see under /dev. We have /dev/com1. So this is there. So I don't know why this didn't work. Let's try again. Some other things. Xconfig, Microsoft. Maybe I take out the baud rate. It could be that this has done something that it should not be doing. Yes, the baud rate was the culprit. All right. So we see here X server is basically running. All right, so I did a little bit of fixing. I think this looks a little bit better, although this is a problem of the screen capture, not so much of the graphics card. And you can see this is kind of working now. Okay, let's try to lower, make this window a little bit smaller. Okay. So let's go here and oops, yeah, okay, that looks fine. Y3. Okay, here the keyboard needs to be configured differently. Okay, here it looks a little bit different. The colors are a little bit off, but fine. Do we have X eyes? We should have X eyes. Yes, we have X eyes here. All right. And Control Z, background. What other applications do we have? User X386 bin. Let's see if I can start Ghost View. Yes, we can start Ghost View. That's yeah, version 1.5. So running on 386 BSD. Nice. This is yeah, the resolution is not the best one. Close this window. Do we have XV installed? Let's see, not found. Let's try to see if I can compile this under /arch. There should be XV. Yes. Let's, oops, ls. Let's see if we can install, if we can compile this. Let's just type make. It's going a little bit slow. You have to remember this is a very old machine. It's a 386 40 megahertz, 40 megahertz, not gigahertz. Yeah. Mm, and it just has 32 megabyte of RAM. The graphics card is having 1 megabyte of RAM. It's an ISA 16, so it's not VESA local bus, not AGP, not anything fancy. It's just well, it is a little bit fancy because it's an ISA 16-bit card. It's not an ISA 8-bit card. So this is why it looks a little bit, yeah, a little bit slow and a little bit different. All right, so it's having some compilation error. That's a little bit strange. It should not have, but yeah, that's interesting. All right, so I cannot show XV, but I can show Emacs with a graphical user interface. This is very appropriate for this system, Emacs, the 8 megabytes and constantly swapping. So it's probably the reason why it's doing, yeah, it's a little bit slow. Hello there. I have no idea how to exit here. Control X, Control C. Yes, it's Control X, Control C. Okay, that's the most important thing to learn in Emacs. Let's see some additional things. Maybe the X logo. That seems appropriate. Yes, this is the X logo. Okay, Control Z. Background. There is the X calc also. Yes, we have a calculator here. All right. And maybe one last thing would be the X kill. Let's run it. Okay, first Control Z, background X kill. Let's yes, we get something here. Let's kill the logo. Yes, then the logo goes away. Great. PS AUX. Let's go back to terminal mode. So for that, I have no better solution than just to kill the X server. So and I'm going to kill the X server and we will see each other already. So back when I reconfigure the terminal. Okay, so here we are, root. We can still ping some, yeah, some interface, some IP address. I think I put here some utilities. We can see the CMD run and transf in the website I'm going to give you, because this is a really old system. It might not, you might have some difficulties running commands as in this system or transferring files. And therefore, I've created, and especially if you're looking at 86 box on the with a slurp interface, that means that it doesn't expose the IP address from the outside. You can communicate from inside the machine to the outside, but you cannot easily communicate from outside to inside. So I created a small CMD run and the transfer. These are basically some small servers that connect to another server running uh, on, for example, a FreeBSD machine or running on Mac or outside the device. And this will allow from another machine to contact this jump host, for example, the FreeBSD machine. When I forgot to say, so when I start the trans for the CMD run, this is a server running on 386 BSD that is going to connect to this server on this jump host, which is going to make the connection from inside to the outside. And someone which wants to contact the machine can then contact this jump host, and it will just relay the either a file that it's going to transfer from outside to the inside, or it's going to run a command. So the transf is to download or upload a file, and CMD run is to run a command on 386 BSD from the outside. So we could run, for example, CMD run. It's going to say, okay, with what is the server IP and which port. In 86 box would be 10.0.2.2, and the Python script that I wrote for the jump host serves typically on port 4444, and this is just going to run without problems. And the transf is also that you give the IP and the port, and it contacts the outside Python server on the jump host. And yeah, we can also transfer files in or out. So let me demonstrate that very quickly. So under my utilities folder, I have for example, the CMD run here, which I'm going to start here with the server. All right. And I'm going to uv run cmd run.py, and this is going to start a server here on the jump host. So it's going to expose something on port 4444 and a netcat on port 5555. So let's open another terminal here, en0. I'm going to get the IP address, it's 187. So let's go again to the 386 BSD machine and run, in this case, it's the CMD run. And we need, let's add a dash v 192.168.2.187 port 4444. That's the default one. And here it's a shell has been spawned and it's connected. So let's see what happened in the macOS machine. And you see here it's a client is now connected. So let's netcat localhost on port. Oops, that's wrong keyboard. Netcat localhost on port 4444. Sorry, there's not port 4444. That's port 5555. Yes. And here now I'm inside this machine. So uname, actually uname does not work. Dmask, and you can see here, yeah, I'm basically, I can run commands as if I would be SSHing into the machine. How nice is that? Yeah, you can see here that this is running CMD run here locally in my Mac, and yeah, I can run stuff here. So Y3, can I? Oh, again, wrong keyboard, and yeah, we are there. Yeah, it's probably Y3 is probably not such a nice command. Okay, probably quit. Yes, yeah, quit Y3. Yeah, it's the terminal is not the best one, but it allows to do some CI CD. Ooh, this concept was not existing when 386 BSD was around. Now, what I would like to show is how to mount floppy drives. So I'm going to put the initial floppy there, and well, it's nicer. Let's just go back to the 386 BSD machine. So here, okay, Control C, I exit. All right, so I've placed the floppy drive in the device, and now we can mount the DOS fs/dev ft0a under floppy. All right. and the GoTech floppy is working. Floppy, and here is the original floppy, which is formatted in MS-DOS format. Can we access the CD-ROM? Yes, we can. In this case, is mount, not umount, is mount ISO file system dev wd1d, if you remember, under slash cd. I created these directories when installing. It should be there. df, we have everything there. ls slash cd, and we see all the programs here. How nice is that? So everything is here. One additional thing, let's see how would we compile the FreeBSD kernel under slash user source kernel. We have the kernel sources here. I think we can just do a make. So let's find dash name kernel kern .mk. I think I'm missing here. Config kernel kern mk. And so we probably need the target. Let's try it. So make target equals 386 PST. Let's see if, yeah, this is basically it. I'm not going to compile everything now because this I think it's going to take quite a lot of time to compile this in the 386 PST machine. But suffice to say that we are going to get a 386 PST kernel in the object directory. And to activate this, we just need to copy it to the root directory. And next time the system boots, we can, yeah, we have the new kernel. So let me Control C here. If you are wondering about the German keyboard and the US keyboard, there should be a driver here named PCCons. Yes, PCCons. So, and you see here there is a .de and .us. Yeah, and diff, let me see, dash s PCCons.c to PCCons.c.de, and it should say that they are identical. So, and compared to the US, there are some differences. So those are the keys that are different between one and the other. This means if you want to compile a kernel with a US keyboard, you can just copy the pccons.c.us to pccons issue make with a target 386 PST, copy the kernel to the root directory, and lo and behold, when you reboot the system, you have the system configured with the kernel for the US keyboard. All right, I think for now it's enough of playing with the 386 PST. I'm just going to go back to the Mac system to discuss a little bit on what I have done to boot the system, what kind of changes I've done to the operating system, and a couple more goodies, and then we should be finished. This video is becoming quite long, but you know, I've been working on this, I think, since at least about 3 months. It has been a long journey until now, and this journey is still not yet finished because, as you see, for example, the kernel is still choking a little bit. It's not very fluid. I do intend to do this, but I'm going to post, as I said in the beginning of the video, I'm going to post the kernel into a repository, also with the CD-ROM. This is a version that yeah, it still has its quirks. It still chokes sometimes. It's still yeah, it's still how do you say? It still breaks. Yeah. From time to time, but yeah, I mean, it's not very stable, but it's an old system, yeah. And I'm very glad that the things I've done until now have been minimal changes from the original 386 PST. I really just wanted to keep as much as possible the original version, so don't modify the artifact too much to honor the past, right? But at the same time, to be able to boot it into, I would not call it modern hardware, but hardware that would be more or less equivalent or available at that time, a 386 machine. Well, that's what the kernel is about, the 386 CPU. But of course, it does have a couple more things. So, for example, my graphics card is a clone. It's not an exact NE2000 card. I don't have. Well, actually, I do have the hardware for an Adaptec SCSI card, but I wanted, if someone wants to boot this, then they should be able to boot this with an IDE. CD-ROM. If you are not able to do these things, I think I need to check on how to post or how to get an ISO file. Sorry, an hard disk image. If I cannot post this because this is a little bit large, in any case, you can use 86 box. It runs pretty nice there. You install in a raw disk and you create, yeah, you create your own disk, which you can then flash into some other hardware and play around. Now let's go back to the Mac system. So let's exit from here and let's have a look a little bit at what I've done here. Well, I'm not sure if what I will be publishing has exactly the same layout. This is the 386BSD boot repository that I created for myself, and it has a couple more things there, but it's probably going to be more or less the same things. So we have the floppy directory where we have the DE and the US versions. Again, a couple of more floppies are flopping around in the breeze here. Actually, not flopping around, flapping around. Yeah, a little bit. In German, you say ein bisschen Spaß muss sein. So a little bit of fun we should be having, right? So these are the two disk images that we need to publish. Those images don't have anything very important, so that they are just simple MS-DOS bootable diskettes that I took from the internet, some MS-DOS, I think 5.0, and I've put inside the boot.exe. That's it. And you can also put a kernel inside the 386BSD kernel to boot directly from the floppy. It takes a little bit more time. Or if you have the drivers for the CD-ROM, well, the floppy boots into the CD-ROM and the boot.exe is in the CD-ROM. The CD-ROM does not boot by itself. It's not an El Torito CD-ROM. So you definitely need anything that boots into MS-DOS that you can access the CD-ROM to start the boot.exe, which is the program that you see here. In terms of the kernel, I do have a couple of versions here. I think that I'm going to release the 452. This represents iteration 52, which is not entirely true. I did use some large language model to assist in some parts of the coding. It has been really problematic to use it. It's too many prompts. I think in total I've done more than 200 iterations, but this is at some point in time when I jumped to version 1.4, I started counting, and this was the latest one, was version 52, and I think I'm just going to stay there. So version 52 is the version that you have in the CD-ROM. It's a DDB kernel, so if you press Control, Alt, and Escape, you get into a debugger. It's still a little bit buggy, so if you press on C to continue and then type in again Control, Alt, Escape, the kernel will reboot. So it's unstable. Yeah, but it did serve a little bit for some things that I wanted to try. And again, I didn't do so many changes into the kernel from the version 1.0. It's unstable by design. 1.0 was and is unstable. Here we have the tar.z. So it's a compressed file, basically. It's in the CD-ROM when you install under /user src kernel, you have version 1.4.52. And I also provide in the CD-ROM the compressed file. Here you see the two kernels. If you want, I've shown how to mount a CD-ROM. So you could also, instead of compiling the kernel, you can just take the German or the English variant of the kernel and just use it directly. All right. So those are the things. The logo, I think I explained. So it's a phoenix rising from the ashes. Unfortunately, I think the Phoenix is going to go down again like the Titanic, because I foresee that less people are going to be using this project, or maybe it's people will start liking this, and maybe it will become a really fun project to revive the 386 PST. But I found it funny to have a Phoenix as a logo, and this has been used, has been generated with the website you see there on the screen. And according to the website, the license is free for commercial usage. This was done on the 4th of April 2026. So here for it's recorded. Under software, this is some software I was porting. So I would like to get DOS-EMU running on 386 PST, because why not run MS-DOS commands? But it requires a virtual 86 mode, which is not supported by the kernel. This is a little bit problematic to do. So yeah, it's asleep, this project, for the time being. Tkern, I don't think that I might publish this, but it's just a very simple kernel written in assembly to test how to boot the system. So these were a couple of experiments on how to enter protected mode and etc. that I was trying. It might be interesting to see. So I think the most interesting part is going to be the utilities. There is an AOut utilities. I'm going to publish this. Let's go to the utilities and AOut. UV run. This is a utility that is going to allow, because this is a relatively old kernel, it uses the A.out format, so it doesn't use an ELF format. And to do some software development, we might want to search for symbols, to search for some addresses, and dump a function in this assembly, etc. And this is just some utility that does these steps. Let's see Calvin. It's the simple VI for MS-DOS. Under CD-ROM, I think I'm going to release this. This is the ISO file that you see here. This is the file that I've burned and that I'm going to provide this to everyone. And there is a create shell here, so that uses MK ISO file system with the appropriate commands to get the things running. All right. So here under all files, these are the files that are on the CD-ROM. As I said, there is the kernel sources here with this name. This on the main on the root directory of the CD-ROM, and it's called 386pst-kernel-v 1.4.52-ddb. All right. Now there is the cmd run. We have seen this. There is a client and a server. So for the client, I think the client is for 386 PST. So this is, you can compile, you can change these things here, and you can have a look on how this is running on 386 PST. And this component will connect to the server part, which is this Python script, the cmd run here .py, and this is going to allow connecting with a reverse shell. The cmd run xz.py is a way that if you run the server, you can just say Python cmd run, command to run, and it just runs and gives you the output, I think from standard output and standard error. Okay, the standard error needs to be redirected like this. This is one great way to make usage of a large language model, that it says, okay, you can connect to the machine and you can run commands on the machine and you can try things out. That's really cool. So have fun with that. There is the install. This is the installer that you've seen that took quite a lot of time to install things. And this is, yeah, it's composed by several pieces here. For example, here is to do partitions. You can you can read all the things that are around here on how to create partitions on the hard disk. I think the important and the interesting thing is on how to do the boot. This is how the system boots. So it shows here the boot flow. The BIOS loads the master boot record from address 0 into 7C00. These are 512 bytes that are loaded from the partition. And this is showing here what is going to be happening in the first stage of the boot process. So there is a relocation, there is a finding of active partition, there is a loading of the WD boot, WD for the Western Digital or an ID drive, and jumps into it. So, and starting from there, the WD boot, which is something provided by 386PST, switches to protected mode and does the rest with the partitions and so on, and fires up the kernel. So, and here, this is the code to install the boot code in the hard disk when we are doing the partitions and so on. And there is a boot advanced here. This is the assembly code. Let's see here. So this is really what goes into the master boot record. We can see here what happens. Yeah. So you can read the things here on wait keys, and so shift pressed, this is when you see the first thing. If you press the shift key, you're going to go into a different partition. So you, in theory, I've implemented this feature but did not test it yet. We should be able to dual boot MS-DOS and 386PST. This is untested and would be fun. Maybe in a future video. Let's see. All right. Yeah, and this is going to do the booting, the boot, etc. This is where you see the yeah, with the boot signature AA55. This is how we know that this is part of the boot partition. The boot advanced.asm, we see here this compiles to 512 bytes, which is the first sector. All right. This is the installer program. The installer program, yeah, it also has some packages, I forgot to say. So here it looks at the CD-ROM. If it has the /pkg, it's going to take the files which are there and copy them, and going to create also files. Yeah, quite a lot of things are going to be put into the system. All right, so this is the installer. There is also the keyboard. So this is the DE, and this is the German version of the PC cons. I might not publish this file or this directory because we have it already in the CD-ROM. We don't need a specific file here. And the patch keys is an idea that I've implemented. So if you have a kernel that is, for example, in having a US keyboard and you don't want to recompile the entire kernel, you can run patch keys. It's going to look for the table in the kernel because it knows the bytes that constitute the table, and it's going to patch it to the German variant. So it patches a kernel without the need to recompile. Dangerous things, so use with care, but that's the main idea. Man to cat, this is to convert trough pages .1.2 to pre-formatted cat pages .0 for the 386PST man page. So we had a couple of software that I ported. For example, I think the Y3 had some pages .1.2, etc. And with this thing here, I was converting it to a man page on 386PST. Nice. All right, the raw write is, I just copied from the internet. So if we would be in 1993 and not having the computers as today, we would get the application, the rawwrite.exec. Yeah, and in the CD-ROM, let me actually go there. CD-ROM, all files. Here, I provide in the /floppy, I provide the 386PST floppy for D, German, and floppy U for the US. And I provide the raw write also with a .text. I think this might be disclaimer, warranty. This is the original documentation and some README showing that this is the German or the United States keyboard. And we would use raw write in MS-DOS to write this image into a floppy, to write this file into a floppy. So if you really want to do things as close as possible to the old days, you can really take the CD-ROM, boot it from an MS-DOS installation, for example, use raw write to create a floppy disk, which anyways you would not need anymore, in the sense that if you can access the CD-ROM, you can just use the boot.exe to start the installation process. But with this, you are able to create a floppy disk for who? For your neighbor, for example. All right, the transf is the again done into two parts. The transf.c, which is the component that gets compiled in 386 BSD and allows to transfer files from the system. So there is a small menu. We didn't really see this. Yeah, there is an MD5. So MD5 is also implemented here. It was not, it was export controlled, so cryptographic algorithms were not, are not in 386 BSD. But we do have some help, and we have some commands that can run local. So local ls, local print work directory, local cd, local cat, local hexadecimal cat, local make directory, local md5, local move, and local remove. And for all these commands, we also have things that can be run on the remote server, and we can put a file. So going from 386 BSD to the server where the transf.py is running, we can get a file. Yeah, so download a file. This would be uploading and this would be downloading. And X is several of them, multiple gets, multiple put, multiple get. And that's it. And for each one of them, we can say help MD, and it will tell you create a directory in the server, how to use usage MD with a directory, etc. So it should be relatively simple and straightforward to use. The transfer.py is the component that runs on Mac or FreeBSD or Linux or Windows or whatever. The www, we have not seen that in the demonstration, but we have here a links server. So there is a links.2.2 and here the binary. We can also browse a server here with the link server. So we would create, for example, a base HTTP request handler. The links vintage server basically just does some downgrades and does some relatively simple things. So that links, this very old version of links on 386 BSD can still get files. So it's another way. If you don't want to use the transf, you can also start a link server. And this is going to allow you to download some files from wherever the link server.py is running into the 386 BSD machine. I don't think this allows to put a file to upload. I think downloading is already there. The last but not the least, there is a config. I'm coming to the boot.c. So, but let's first look at the config file. The config is an interesting program. So you can say config and the kernel -scan. So let's first look at what the scan is. Let's go here to the user. So let's go to the kernel sources. User source source kernel. Let's go, for example, for the WD. WD is for the Western Digital. Is the IDE disk. And the original file here was the original from version 1.0 from 386 BSD, and then there's the -.c, the file that I modified. And you can see many of the devices, they have the configuration here, WD032 and etc. etc. So what this is basically saying, without too many explanations, is that the controller is for the WD device, Western Digital, for the ID interface, is running on, the first one is running, so WD0 is running on IRQ14 and IO port 0x1F0. The second one is running on IRQ15 and port 0x170. And if we modify this string here, if we modify this thing here and recompile the kernel, then we can change this configuration. So that's the main idea. Let's go for the ED. ED here. And under the ED, we can see that ED, we have port 0x300 IRQ10. And there are a couple more things here, but yeah, that should be for now enough. So there is one network, so it ends with a dot here, and it's currently configured for IRQ10 and IO port 0x300. This is hard coded into the kernel, right? So what we do here is we look at the kernel, a compiled kernel, and look that this is dangerous, what this config is doing, but it's basically a configuration tool to change those strings without recompiling the kernel. So we can scan the strings inside the kernel because we know what the devices are, and we can kind of have an idea about some expressions on how to search them. And we can patch the device with some configuration, or if we know exactly the offset, we can even say, well, patch at this offset. Really dangerous. Again, repeating the things is we should not just patch things at random offsets, because here, yeah, we can really screw the kernel. Let's say here are a couple of examples. So for example, if we want to change here, we might want to change the ED device to 0x300 IRQ number 5, and we could use the patch functionality on the config without recompiling the kernel. -X would disable the device, and -U restore to its original configuration. So you might want to look here how this is working, and you can either use this file or you can just recompile the kernel. It's probably easier because this is done probably only once, right? Note that all of these files here, you can compile with cc-o config.c under 386pst, but you should also be able to compile these files under MS-DOS with Borland C++. All right, we are coming close to the boot.c. That's a relatively large file, and the boot.c does have quite a lot of things inside. And don't forget, the boot.c is a file that is going to be compiled with Borland C++ 3.1 under MS-DOS. The idea is really to start the kernel to bootstrap the whole thing so that we can start installing 386pst. We need to first boot into the system. So it means we need to load the kernel into memory, we need to enable protected mode, and we need to jump into the kernel. And when we're starting the kernel, switching to protected mode and so on, one of the most important things that we need to tell the kernel is, where is the root file system? Yeah, that's why you see in the very early beginning of the video that I say boot and the root device. So because the kernel needs to find the init program to start, right? And for that, it needs to know what is the root file system. All right, so here is the usage for this program to do the bootstrapping. You write boot kernel, S or M, S to boot into single user mode, or -M to boot into multi-user mode. Why would we want to boot into the multi-user mode? Let's imagine that you installed 386pst And for whatever reason, you recompile the kernel and copied it to the main directory, and suddenly your system doesn't boot again. What can you do? Well, you boot with a floppy, you go to the CD-ROM and you type in boot, yeah, with the kernel that you know it's good, and you go to multi-user on your root file system on your disk because you know your disk is good. It's just the kernel that has a problem, and you should be able to boot properly. And then you can just copy the kernel again to the disk, or you can recompile the kernel. And how do they say, Bob's your uncle, right? So you can start fixing your system. All right, so -r with the root file system would be, for example, WD0A if you are repairing the Western Digital disk. If you install the operating system on a SCSI drive, that would be AS0D. Sorry, the D, I think the D is for a CD-ROM. Yes, that would be for a CD-ROM. If you installed it in a SCSI drive, it would be AS0A, I think. So the UFS is you're basically telling when you're initializing the kernel, you are saying that you want this to be it's a UFS file system, the root file system. If you say -isofs, then you say, well, my root file system is an ISO file system. The kernel needs to know that in order to call the appropriate routines to mount the file system. The -t is going to list known devices with the names, so WD, AS, and so on. And the stuff I've shown before with the config, I was saying config.c needs to be compiled under MS-DOS. Well, no. Actually, the configuration, all the settings that are in the config are also in the boot. So you have the scan, the patch, the find, -x, and -u. So you can also use boot, the boot.exe. In MS-DOS, you can also use it to patch a kernel. So if you want to boot, if you want to create a modified kernel that somehow connects to your network card on another IRQ address, you can do it from outside without rebooting, without putting into 386 BSD and without compiling the kernel. All right, and here is a small explanation on how things are going. So saying that you don't need to have high memsys installed. It's just going to use interrupt 15 function 87 hexadecimal, which is a BIOS call. It's going to build a minimum GDT, the global descriptor table, to enter the protected mode. And it's going to do here the stages. So I'm not going to say everything in very much details, because yeah, it would take quite a lot of time to explain how the system basically boots. But if you want to spend some time, you can look at boot.c. It does everything. I mean, it goes from it's not from the master boot record. For that, you can see the installer with the other program from the master boot record. Works slightly different, but still does the same thing at the end, right? Here is it does it from MS-DOS. You need just to be a little bit careful on how to load the things. For example, skipping the ISA hole, etc. Yeah, and it's going to look at the lowcore.s in the operating system. All right, so here a couple of options: boot single, boot multiple. Here, how the things are encoded to create a boot device, how the flags look like, that it's a flag that's put in the stack before we call the kernel. So the kernel knows what is, where is the operating system, where is the root file system, and etc. Good, and basically, let me see CMOS read. So here, there are a couple of functions here that use the BIOS, for example, to know how much memory the system has. And here we see one of the most important places for the boot part, which is the GDT to enter the protected mode. And we see here the protected mode GDT. so zeroth entry is a null. The first, the entry 1 basically configures here the base and the limit and etc. So this is a standard thing on entering protected mode. And here the protected mode stub. This is code that is written partially in assembly and here with an explanation on how things are working. And yeah, let's see here. So it's here initializing the segment registers. This is, there are a couple of messages, so a couple of callers, a couple of things that are written to the video memory that are just to make sure that the boot is executing correctly. So it writes a P and so on. You might have noticed that when booting the kernel, this is on the boot.exe to make sure, okay, we arrive at that point and we arrived at that point. So here we write a P, then we mask all the peak interrupts. So this is the programmable interrupt controller. And mask also meaning disable them all. And enable the A20 gate to be able to address the memory. Yeah, so here the explanation. Then we have some phases. Here we copy the first stage. Then we write one. Phase 1 is completed. We do the second phase and we write VGA phase 2. If there is any issue and the computer would stop there, then we would see, aha, we have an issue. Houston, we have a problem. We zero out the BSS, write B. B is done, the BSS, and we jump. And here, well, we should we write the J. Yeah, the J is actually before we do the jump itself. So here you can see we push the boot device and the how to. This is the information on how the system is going to boot and what is the boot device, where is it? Yeah, what I was saying before. So this is the low core. It basically jumps to the low core that is expecting those values, and we print the J in the boot, and there we go. Here is jump into oblivion. This is we are gone here. After this, we lost control. This is after jump EAX. So if you see here XOR EAX, this is basically saying, well, EAX is loaded with the value 0. And then jump to this 0 means bye-bye, we are in kernel land now. We are no longer running MS-DOS or anything. I mean, at this point, we were no longer running MS-DOS. This is already in the protected mode, but here is really, we are gone. So long! So that is really the point where we enter the kernel. And here you see also the exact kernel is the point of no return. Yeah, so, and we see a very nice description. Step 1, disable interrupts. Step 2, load the flat, that was the GDT that I was explaining before. This is a flat 32-bit GDT, means I load the entire memory. Sets the PE via some instructions, the protected mode enable, and then does the stub, so enables the A20 gate, copies the kernel. So here, when we enable the gate, then finally we are able to address more memory than the 640 kilobyte, and we start copying the kernel into a staging area. It's the kernel, basically the idea from 386 BST, you load the kernel into memory address 0, starts at 0. The kernel will do a relocation afterwards. It will relocate itself again, but this is no longer under our control. The low core expects the kernel to be loaded at address 0. And I think I'm going to show this in soon, although the video is becoming a little bit long, but I think this is worth to mention in the video. Yeah, so we start loading the kernel at address 0. We have the hole here, then we put the zeros, we push the how to and the boot dev, and we go for the point of no return. We jump to address 0, the kernel entry, and that's it. And the kernel starts doing its business. So this is the explanation here. So the PM stub is a couple of things. It's the GDTR, Global Description Table. I think it's called this name here. And yeah, it's a couple of things need to be patched by hand, which is, yeah, it's basically all explained here in this code. I think it's pretty cool and pretty nice to see this. Here is the usage, the parsing of the arguments, and that's it. That's boot.exe. Okay, so this is how things start. Now let's just try to see a little bit on about this low core business that I was talking about. So, and for that I have here a book which is the Bible of 386 PST. It's interesting that the video is going to end with the beginning of the thing. So it might be the beginning of the end or the ending of the beginning. I don't know. Yeah, we'll figure out. All right. So this was a book which is called "The Basic Kernel Source Secrets." Was written by William Jolitz and Lynn Jolitz, his wife. This is available on archive.org. And this explains in very much detail how the system is working. Let me see. And here it starts on page 29, the assembly entry primitives, explaining exactly where do we go from here. You remember the point of no return? So here is exactly where do we start. And let's have a look at the description here. So page 29. So there are some really good explanations here. And here is chapter 2, assembly entry and primitives. Here it explains a little bit on historical origin and how the context switch mechanism is working. And here again, the interrupt control units, etc. Here is how the kernel looks like. This is the out file format. So we have text. So this is the instructions. We have initialized data. This would be static data, for example. The BSS, the part that is initialized with 0, and the config, which I've not been able to figure out for as yet, but I have the feeling this is not really implemented. But it's currently working. Yeah, my boot.exe doesn't take into consideration the config here. So maybe this is a point to improve. Yeah. So bootstrap tracks, so configuration strings here. So it's probably some more clever way other than rewriting the configuration strings that I was saying before, that the config.exe or the boot can change in the binary file of the kernel. Probably this is a better way to do some other configuration. It's more work to find out what this is doing. And it starts explaining here about the base memory of a computer, 640 kilobytes of RAM, and how does it look like? So this is the physical memory layout during the start. And it's probably going to show that, well, let me see if I can see this thing here, ptmap low core. And there we go. What does start expect of the bootstrap? Start expect, so the start is the function that gets called. Start expects that the bootstrap will load the kernel program into memory starting at address 0 and successively occupying space in physical memory. And then here, start code then rejoins as we were seeing in the bootstrap code or boot.c. Uh, there is a hole there that needs to be taken into consideration, and this book here explains exactly what this is how to deal with that. So kernels larger than 640 kilobytes. For those kernels, the bootstrap will continue to load memory above this hole. So this is the ISA hole. And one of the first tasks of the start code is to rejoin this hole in the virtual address space. And here the bootstrap passes the arguments, the boot flags, the boot device, and the kind of file system, which is, yeah. Oh, and where the hole starts. Okay. So I think the where the hole starts, it's this was planned in the book here, but according to the code that I've looked at, this is it's not really necessary. It's at a fixed position, so this is why this parameter is not passed. The boot device is used to determine where the initial root file system may be found, and etc. etc. So it's really nice to read here about how this is working here with yeah the different functions, how the boot process is basically working. Yeah, so I think I've done quite a lot for now for the video. It has been quite a lot, quite a big journey. If you manage to follow me until this point, yeah, it's we went through lots of things together. Yeah, and you see, I put quite a lot of effort and care about the 386 BSD because this is the grandfather. No, actually, I don't think it's the grandfather. This is the father of FreeBSD. Yeah, the grandfather would be the original one that ran in the PDP that could not put in 386 Intel CPUs. But this is Papi. This is Papi, right? So I put some effort here to try to make sure that things are preserved. They are still not 100% good, so it's the kernel still has some hiccups from time to time, but yeah, when I have time, I might be contributing something to the project. And if you also want to do some things, you can also fork the project, just have fun with this and maybe improve the kernel yourself if you have time. And if you do that, I would really like to hear about the improvements you've done because I would like to test them out again. Maybe in some future videos I would like to test out. That would be really cool. One of them I have it already running, but I didn't show in this video. It's way too long already, which is an old version of Wine, which is compiling in 386 BSD and should be running also. So we should be able to run Windows applications from Windows 3.1, I think, under 386 BSD. How awesome is that? And the other thing, maybe I need to use some large language model or something to try to get the virtual 86 mode implemented in the kernel to be able to port DOS EMU. That would be really cool if we could run MS-DOS commands directly inside 386 BSD. Last but not the least, jails are not implemented. For sure, they are not implemented in 386 BSD, but there is another technology that's implemented that is chroot. And I would like to experiment a little bit with chroot. Of course, it's not the same as a jail, but it's something that is implemented a long time, and I would definitely like to see that running. I think chroot is implemented. I'm like positively sure that chroot is implemented. If it is not, well, it is what it is. So I think this video, as I was saying, is really, really long. If you have been chugging along, so thanks for keeping up. Thanks for being there, for putting up with me all this time. And yeah, I'm going to publish the code. And if you have additional comments or suggestions, you know already, use the space down below, right? Thanks a lot for passing by. Take care. See you next time. Bye bye.